Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch my videos on my channel. Today also we are continuing the discussion of open channel flow. Flow in open channel may be either uniform or non-uniform. In uniform flow, the depth of flow remains constant along the length of the channel. So this type of flow is possible only for prismatic channel of sufficient length. In non-uniform flow, the flow characteristics, that is flow velocity and flow depth, are changing in the direction of the flow. Whether this variation is in small rate or in large scale, it varies in the direction of the flow. Non-uniform flow is classified into gradually varied flow and rapidly varied flow. In gradually varied flow, normally we are referring as GVF, flow depth changes in the direction of the flow. Or we can say that gradually varied flow is a steady non-uniform flow in a prismatic channel with gradual changes in its water surface elevation. Since the flow characteristics are changing gradually, there is minimum energy loss. So that is why we can use energy concept for the derivation of dynamic equation of gradually varied flow. In rapidly varied flow, flow characteristics like flow velocity and flow depth changes rapidly for a short distance. One of the best example is hydraulic jump. In hydraulic jump, flow depth as well as flow velocity changes suddenly over a short distance. Figure shows a combination of rapidly varied flow and gradually varied flow. Water which overtops a spillway and it becomes rapidly varied flow because of the sudden change in the flow characteristics. Then it becomes a gradually varied flow by flowing over a mild sloped surface. So again the slope changes suddenly. So this flow becomes rapidly varied flow. Then it becomes uniform flow because of the constant slope for a certain length. A lot of turbulence occurs due to the rapid variation in the flow characteristics contribute large amount of energy loss. So because of this high energy loss, we cannot apply the energy concept because this energy loss is unaccountable. So that is why for the analysis of rapidly varied flow, we are using momentum concept. So in this class, we are first discussing about the gradually varied flow and the computation of the length of the gradually varied flow profiles. So gradually varied flow, as we had discussed earlier, it's a steady non-uniform flow in a prismatic channel with gradual changes in its water surface elevation. Gradually varied flow may be caused as a result of the change in size and shape of the cross-section of the channel, change in bed slope, obstruction in the direction of the flow, that means due to the construction of the weir or dam in the flow direction, and change of roughness or change of frictional force at boundaries. So these are the main reasons which causes gradually varied flow. Now let us discuss the importance of analyzing this gradually varied flow. In the design of open channel, it may be necessary to calculate the flow pattern for getting the surface profiles and the length over which backwater effects due to the construction of hydraulic structures like dam, reservoirs, weirs, etc. As we had discussed earlier, the analysis of open channel flow is very complex due to the effect of natural factors, the variation of surface roughness, change in cross-section in the direction of the flow. We have learned previously about the formation of M1 profile and M3 profile for a mild slope channel. So M1 profile mainly occurs due to the obstruction in the form of weir or dam, whereas M3 profile occurs mainly due to the lifting of the gate in a reservoir, and M2 profile forms due to the sudden cut in the bed slope. Since flow characteristics varies gradually, gradually varied flow occurs for a long distance. The dynamic equation of gradually varied flow, that is dy by dx equal to S0 minus Sf divided by 1 minus q square t by ga cube. This we have derived based on certain assumptions. The first one is bottom slope of the channel is very small. Then the channel is prismatic. Then energy correction factor is unity. So within this condition, we can say that pressure distribution in any vertical is hydrostatic because for a small sloped prismatic channel without the turbulence, the streamlines are straight and parallel. So in that case, the pressure distribution in any vertical is hydrostatic. The next one is roughness of the channel is constant and it is independent of depth of flow. So within these conditions, we can apply uniform flow discharge equations for the computation of energy slope. That means we can use Manning's equation or Chassis equation for the computation of the slope of the energy gradient. So the computation of gradually varied flow profiles involves basically the solution of the dynamic equation of GVF. So the main objective of the computation is to determine the shape of the flow profile. So what is the necessity of computation of length of gradually varied flow profile? So whenever we are constructing a dam across the river, it rises the water at the upstream side of the dam. So if we are not giving enough protection to the sides of the river, the water overflows to the river bank and it will destroy the other structures. So that is why as a hydraulic engineer, one has to determine the length of this water surface profile. Hence, in the design of the open channel, it may be necessary to calculate the flow pattern for getting the water surface profiles and the length over which backwater effect due to the construction of the weir or dam. So length of the flow profile is calculated from the point of disturbance. So how will you find out the starting point? So the length of the flow profile is to be calculated from my starting point. That starting point is called control section. So control section is a section where a definite relationship between depth of flow and discharge exists. So in the control section, there is a definite relationship exists between Q and Y. So critical flow is a control section. Similarly, the position of the gate, weir and sudden force, etc. are also the control section. Wherever there is a definite relationship exists between the stage of the river and the discharge, and that section we can assign as the control section. Or a control section is a suitable site for measuring the flow in a channel. The flow is identified as critical flow, subcritical flow and supercritical flow based on fruit number equal to 1 is for critical flow and fruit number is less than 1 for subcritical flow and fruit number is greater than 1 for supercritical flow. Subcritical flows are affected by the change in the downstream condition. So that means control section is located at the downstream. So this can be explained with this diagram. So in this figure, S0 is less than SC. That means the slope is mild. So for mild slope channel, subcritical flow is possible. Here this flow profile is found due to the construction of the dam. So that means the flow condition at this point is affecting the flow in the upstream direction. So at this point, there is a definite relationship exists between the discharge and flow depth. So that is why the computation is starting from this point towards the upstream side. That means for a M1 profile, the computation is starting from this point towards the upstream side. Similarly, for this M2 profile that is also occurred in the mild slope channel. From this figure, you can see that M2 profile is crossing the critical flow section. At this point, the flow is critical. That means a definite relationship between the discharge and depth is available. So the computation is starting from this point towards the upstream side. So whenever there is a subcritical flow, then control section is located at the downstream point. So in this figure, this portion is slope is less than 0, that means adverse slope, and this side slope is greater than critical slope, that means steep slope. So here the possibility is A2 profile and here the possibility is S2 profile. So the flow in a steep sloped channel is supercritical flow. So supercritical flow is always affected by the change in the upstream condition. So for the computation of the length of S2 profile, the control section is located at the upstream side and the computation is proceeded towards the downstream side. Whereas for A2 profile, this portion is subcritical condition. So subcritical flows are affected by the change in the downstream condition. So the computation here is starting from this point towards the upstream side. So here you can see that this portion is mild slope channel and this side is steep slope channel. So the control section is located at the point of change of slope. So this is the point where the slope changes. So S2 profile is computed from this point towards the downstream side because here the flow is supercritical. Whereas for M2 profile, the computation is starting from this point towards the upstream side because here the flow is subcritical. So by identifying the flow as subcritical or supercritical flow, we can identify the location of the control section. One should classify the slope and identify the flow profile, then locate the control section. Then we have to compute the length towards the upstream side if it is a subcritical flow, and towards the downstream side if it is a supercritical flow. In the next section, we can discuss about the computation of length of water surface profiles. In the direct step method, the channel is divided into short reaches and the computation is to be carried out step by step from the control section. The figure shows a portion of the channel between the two sections 1 and 2, which is at a distance of dx apart. S0 is the bed slope and SF is the slope of this energy line. HF indicate the head loss between the two sections, which is equal to SF into dx. By balancing the energy between the two sections 1 and 2, we can write y1 plus v1 square by 2g plus z1, that is equal to y2 plus v2 square by 2g plus z2 plus hf. If we are considering the line which is coinciding with this section 2 as datum, then z2 equal to 0, then z1 which is equal to s0 into dx, and hf we are replacing by means of sf into dx. So this equation becomes y1 plus v1 square by 2g plus s0 into dx equal to y2 plus v2 square by 2g, and z2 is 0 and hf is replaced by sf into dx. Now what is y1 plus v1 square by 2g? y1 plus v1 square by 2g, that is the specific energy at the section 1, and y2 plus v2 square by 2g, that is the specific energy at the section 2. So if we are replacing this term by E1 and this term by E2, this equation can be rewritten as E1 plus S0 into dx equal to E2 plus SF into dx. So this can be written as S0 dx minus SF dx equal to E2 minus E1, that is equal to delta E, or dx equal to delta E divided by S0 minus SF. This is the principle of this direct step method. So we have to calculate delta E between two sections, and that delta E divided by S0 minus SF will give you the distance between the two sections. So this method we can apply continuously from section to sections. Then we can compute the total length of water surface profile L equal to sigma delta x. The accuracy of the computation increases by lowering the value of dx. Now the session comes to an end. So we started with the classification of non-uniform flow as gradually varied flow and rapidly varied flow. So in the design of the open channels, it may be necessary to calculate the flow pattern for getting the water surface profile and the length or which backwater effects due to the construction of the dam or any other hydraulic structure. So we continued the discussion of the computation of length of the water surface profile by direct step method. We also discussed about the location of the control section for subcritical flow as well as the supercritical flow. For the time being, it is enough. Thank you.